In this example, we have a drug company who supposedly came out with a drug that destroyed cancer cells in a safe manner. And they claim that there's a 71% chance that one would be cured using their drug. A skeptic doctor believed that they may be just making this up to try to boost their sales, and they believe that percent was lower. So this doctor took a random sample of 88 people and found that 55 are cured of the cancer. Let's conduct a full hypothesis test testing this claim. We're going to use an alpha level of 0.05 or 5%. To start off our hypothesis test, we're going to write our hypotheses, and our population proportion we assume equals 71%, or probability of 0.71. Our HA is that the proportion is less than 71%, or probability of 0.71. Now, before we go further, though, we should check our conditions to make sure this is a valid hypothesis test. Our conditions say we need a random sample, right? So a random sample, I'm just going to write RS, and we do, random sample. We need to have our second one is our sample size times pi needs to be greater than or equal to 10, which this quantity is. Our sample size times 1 minus pi needs to be greater than or equal to 10, which it is. And our sample size needs to be at less than 10% of the population. And less than 10% of pop. Now, this is something we don't know, but we can assume that there are more than 880 people with cancer. So let's kind of put a check there. So our conditions are rocking and rolling. We can have a valid hypothesis test results. The next thing that we should do, right, is find our test statistic. So to find our test statistic, again, we thought of that as a z-score, so I'll just write parentheses, it's z-value. We're going to take our sample proportion, right? And our sample proportion we can find by looking at this ratio, 55/88. And this comes out to be 0.625. So we'll take that sample proportion, and we're going to see how many standard errors is it from our assumed population proportion. Right, we're assuming the population proportion is 71%. That's our assumption. We're assuming that's the case. How many standard errors away is it? Well, let's find our standard error. Our standard error is assuming we know the population proportion. So we're going to use that population proportion in our standard error because we assume we know it. And we'll put that in terms of our sample size, which was 88. Just to be clear, all of this is under the radical. Cool. If we were to do this out, we end up with about negative 1.77. Over here, I'm going to draw a distribution. And something like this. And we have two different distributions we can think about these things in terms of. We can think about in terms of our distribution of sample proportions. Or we can think about things in terms of the distribution of our standardized distribution, our z distribution. And what we did is we took this sample proportion, 0.625, and we turned it into the z value, negative 1.77. The mean of our original distribution we're assuming to be 0.71. That was our assumption. The mean of our z distribution is 0. Now, since our HA is less than, remember our HA is less than, to find our p-value, we would look for all of this shaded area. And that would be our p-value. To do that, we'll go to our distribution calculator. Here we have our distribution calculator, and all we're going to do is input the value negative 1.77. Cool. But we don't want this stuff greater than, right? Our HA was less than, so we'll look for all the area less than. And if we do that out, we end up with a p-value of roughly 0.0384. 0.0384. And that is the value that we're going to use for our test, 0.0384. So I'm going to use that value for our test. Cool. That is our p-value. And all we'll do is we'll compare our p-value to versus alpha. So we have p-value versus alpha. And alpha in this case was 0.05. Our p-value is 0.0384. So we find our p-value is less than alpha. Since our p-value is less than alpha, now we want to say, well, what evidence does that give us? So I'll write evidence. And this says we have enough evidence to reject our null and to support the alternative. That the population proportion of cancer patients who will get cured using this drug is less than 71%. We have enough evidence to support that. Now let's kind of interpret some of this stuff that we just went over. Our test statistic, right? Our negative 1.77, our test statistic is saying that our sample proportion, 0.625, is 1.77 standard errors, right? Because this whole function right here is our standard error. It's 1.77 standard errors below our population proportion, our assumed population proportion. How different is our sample proportion from our population proportion in terms of standard errors? Well, it's 1.77 standard errors below our population proportion. That's how far our sample proportion is from the population proportion. If we wanted to interpret this p-value, and I'll write it as a percentage because I think students like thinking of it as a percentage, 3.84%. What this p-value is saying is there's a 3.84% chance of what? There's a 3.84% chance that we would have gotten our sample proportion of 0.625 or one more extreme or one less if what? If our null hypothesis is true. So if in fact 71% of cancer patients will get cured from this drug, if that is true, and that's how we set the center of this distribution to where we did. That's why the center is at 0.71. If that is true, then there's a 3.84% chance we would have gotten this sample proportion, 0.625, or one less. It was very unlikely for us to have gotten that sample proportion or one less if in fact 71% of patients would get cured using this drug. We can think about it in terms of a z-score. If in fact 71% of cancer patients will get cured using this drug, there was a 3.84% chance we would have gotten this test statistic, or one more extreme, or one less. So you can think about your p-value in terms of your sample proportion or in terms of your test statistic, your z-score. Now let's see what would happen if we change our HA. Imagine instead we wanted to test the claim that the proportion is just different from 71%. It's just different. Could be bigger, could be smaller. So what is going to change here? We still end up with the same sample proportion, 55 over 88. Therefore, we're still going to end up with the same test statistic, negative 1.77. So we would graph our test statistic, we would graph that sample proportion, and then what area do we look for? Well, since we don't care if it's bigger than or smaller than, you may think to yourself, well, what if we look in less than and greater than? Well, if we were to do that, every single time our p-value would come out to be 100%. If we looked for everything less than and everything greater than, our p-value would always be 100%. We shouldn't be looking for less than and greater than from our exact test statistic when our HA is does not equal to. We need to do a little bit something else. And here's how/why we do what we do. I'm going to draw a new distribution. But this time, we're going to be interested in using or thinking about alpha. Right? We need to support HA, or we should support HA if our proportion is bigger or if our proportion is much smaller. We don't care if it's bigger. We don't care if it's smaller. We're interested in both sides of our graph. We need to support HA if it's much bigger or much smaller. Previously, we only cared about it being smaller or we cared about it being bigger, one or the other. Now we care about both. Here's what we technically were doing using alpha before. Over here, I'm going to draw a little red line, draw little red lines. And think of this as some value associated with alpha. And everything to the left is 5%. Everything to the left is 5%. And what that would be saying is anytime you got a sample proportion inside of this region we created, in this 5% region, your p-value would be less than alpha, and you would have enough evidence to support HA. If your test statistic fell to the right side of your red line that you created, you would have not received an extreme enough test statistic or sample proportion to support HA. And we only cared about being small, right? We were only trying to show that it was less than 71%. So we can put all of our region, all of our alpha, we can put to the left side of our graph. Those are the more extreme test statistics that support HA. Well, now that we don't care about being bigger or smaller, what we would have to do is we could put alpha over here, a small test statistic should support HA, and alpha over here, a big test statistic should support HA. We're now worried about both sides of our graph. But there's a problem in doing this. If we put 5% to the left and 5% to the right, in total, that would give us an alpha level of 10%. And we don't want a 10% chance of making a mistake, a type 1 error. We only want a 5%. So here's what we'll have to do. We'll have to create new regions where we split up alpha. Half is on the right, half is on the left. We have to split up our alpha into two halves because we're interested in being bigger or smaller. Now, collectively, we have a 5% alpha level. So this is what happens when we have a does not equal to HA. We have to split up our alpha level to both sides. And because of that, some interesting things happen. Previously, we ended up with a test statistic of negative 1.77. And we found that all the area less than negative 1.77 is 3.84%. Notice our test statistic did not fall in that region. It did not fall in that alpha created region. So because it did not fall in that alpha created region, we should not support the HA based on this does not equal to hypothesis. It didn't fall in that region. Yet, if we look at our p-value and compare it to alpha, our p-value is 3.84% and our alpha is 5%. Our p-value is still less than alpha. But again, our test statistic didn't fall in our extreme enough region that we created. So we should not support HA. To counteract this, what we do is we create another test statistic, a positive version of our test statistic. So whenever you have a does not equal to HA, so if HA is does not equal to, we create a positive and negative version of our test statistic. And we'll look at the more extreme area on both sides. Everything less than the negative and everything greater than the positive. And we do this splitting up because we split up alpha into both sides of our graph. So it would only be fair to do this to our p-value. Since this is a symmetric distribution, everything that's going on the left would be exactly what's going on the right. Our p-value would be this collective area, which would come out to be 7.68%. This would be our collective p-value. And now we'll find that our p-value, that it's 7.68, our p-value is greater than alpha. And so what that tells us for our evidence is not enough to reject HO and not enough to support HA. We don't have enough evidence essentially for anything since our p-value is greater than alpha. It's kind of interesting that many times you may need a more extreme test statistic to support an HA of does not equal to. Intuitively, you may think it's easier to support that claim, just being different than 71%. Now, you still have the same type 1 error rate of 5% if you held that constant. But because you split up your alpha level into both sides of your graph for does not equal to, the value of your test statistic needs to be more extreme than if you were solely interested in a less than or greater than. And that's because you put all of your alpha into one side of your graph for a less than or a greater than, a one-tail test. You split up alpha into both sides of your graph for a two-tail test. So we see we did not support an HA of does not equal to, but we did support an HA of less than. This is how we can use these directional hypothesis p-values to test our claim. And depending on what the HA is, affects what the more extreme values are.